Assalamualaikum warahmatullahi wabarakatuh. Hi, my name is Bima Satya Kurnianto. My NPM is G1D021035. I'm from class A. In this video, I want to reading text about electromagnetism. Problems involving conductors are of slightly different nature than those we've discussed up until now. The reason is that we don't know from the start where the charges are. So we don't know what charge distribution P that we should be solving for. Instead, the electric fields from the other source will cause the charge inside the conductors to shift around until they reach equilibrium in such way that E equals 0 inside the conductor. In general, this will mean that even natural conductors end up with some surface charge, negative in some areas, positive in others, just enough to generate an electric field inside the conductor that precisely cancel the due external source. An example, a conducting sphere that illustrates the kind of problem that we have to deal with. It's probably best just to give an example. Consider a constant background electric field. It could, for example, be generated by two charged plates of the kind we look at in section 2.1.4. Now, place a natural spherical conductor inside this field. What happened? We know that conductors can't suffer an electric field inside it. Instead, the mobile charge in the conductor will move, the negative ones to the one side, the positive ones to the other. The sphere now becomes polarized. This charge contract the background electric field such E equals 0 inside the conductor, while the electric field impinges on the sphere at right angles. The end result must look qualitatively like this. We'd like to understand how to compute the electric field in this and relate situation. We'll give the answer in section 2.4.4. An application Faraday cage. Consider some region of space that doesn't contain any charge, surrounded by a conductor. The conductor sits at constant P equals P0. While since there are charges inside, we must have 2P equals 0. But this means that P equal P0 everywhere. This is because if it didn't, then there would be a maximum or minimum of P somewhere inside. And we know from the discussion in section 2.2.5 that this can be happen. Therefore, inside the region surrounded by a conductor, we must have E equals 0. This is a very useful result if you want to shield a region from electric fields. In this context, the surrounding conductor is called a Faraday cage. As an application, if you're worried that they are trying to read your mind with your electromagnetic waves, then you need only wrap your head in tin foil and all concern should be alleviated. 2.4.1 Capacitor. Let's now solve the electric field in some conductor problems. The simplest example are capacitors. There are a pair of conductors, one carrying charge Q, the other carrying charge minus Q. Parallel plate capacitor. To start, we'll take the conductors to have flat, parallel surface as shown in figure. We usually assume that the distance D between the surface is much smaller than A, where A is the area of the surface. This means that we can neglect the effect that arise around the edge plates and were justified in assuming that electric field between the two plates is the same as it would be the plates were infinite in extent. The problem reduced to the same one that we considered in section 2.1.4. The electric field necessarily vanishes inside the conductor, while between the plates we have the result in 2.10. E equals sigma by epsilon 0 times Z where sigma equals Q divided by A, and we have assumed that plates are separate in the Z direction. We define the capacitance C to be C equal Q divided by V, where V is the voltage of potential difference, which is, as the name suggests, the difference in the potential P on the two conductors. Since E equals minus dP divided by dZ is constant, we must have flux equal minus Ez plus C to V equals flux 0 minus flux D equals Ed equals Qd divided by A epsilon 0. Because V was proportional to Q, the charge has dropped out of our expression. For the capacitance, instead, C depends only on the geometry of the setup. This is general property. We will see another example below. Thanks for watching. Wassalamualaikum warahmatullahi wabarakatuh.